Is Milan seal, and so we will know why binding energy is a fundamental parameter to model interstellar chemistry.
Hi everyone, good afternoon. I am Milan Sil from India, and now I recently in the last month I got my PhD degree, and now I am associated with SN Bosch National Center for Basic Sciences, Kolkata, as a postdoctorate research associate. And today I will present our important work on binding energy, which is a fundamental parameter to model interstellar chemistry. So basic processes on interstellar grain surface, the adsorption, desorption, diffusion, and reaction. So these four processes are occurring in dense cloud environment on grain surface. So grains are actually important to form the complex organic molecules. So accretion occurs, then reaction occurs, and desorption and diffusion are the main characteristics to linked with binding energy. So binding energy is important for the complex molecules formed on grain surface, and that is freeze out to the outer part of the protoplanetary disk. So it is linked with the snow lines. It depends on the freeze out of the species on protoplanetary disk in the late evolution phase. So binding energy, we calculated the simple formula quantum chemically. These are the optimized energy of this surface and species complex. Actually, this is single surface and this is species. So this is a simple example that is the gas phase species hydrogen and carbon atoms. They adsorb on interstellar ice mantle, and then they react to form methanol, and then they dissolve via non-thermal or thermal desorption mechanism, and we detect by reobservation in the gas phase. So finding the binding energy of H and H2 on different grain surface, we first use benzene as a grain surface. Why we took benzene? Because we know the graphite is the important carrier of interstellar grain core. So to mimic the graphite, we use a benzene to mimic the graphite, and for the benzene we get hydrogen binding energy of 217 Kelvin and H2 binding energy 315 Kelvin, and for silica we get 580 Kelvin for hydrogen atom and 1090 Kelvin for H2 molecule. And why we take silica? Because it mimics olivine type grain surface. So we took silica of three silica molecule cluster to mimic this olivine type of grain. And next we use the most abundant interstellar grain mantle, water, and for this we took 6 water molecule cluster and calculate the binding energy of hydrogen as 181 Kelvin and 545 Kelvin is for H2 molecule. So for all the cases, we can see that the binding energy of hydrogen is less than that of H2. Where some literature values says other ways, that is the H2 is smaller and H is greater binding energy. And for choosing the grain surface structure, we consequently increasing the structure of water molecule, dimer, trimer, tetramer, pentamer, and hexamer. And why we take water? Because water is the most abundant interstellar ice components, and there are several other studies in the literature where some molecular dynamic simulation taken to construct the amorphous ice cluster model and also crystalline ice structure model. So we took this structure and check how binding energy vary. So in this plot, here total 16 blocks are there for 16 stable species, and red line indicates the zero deviation from the experimental values of binding energy. So with increasing cluster size, x-axis is the increasing cluster size, the binding energy deviation is decreasing. So for 5 and 6 cluster size, the binding energy is decreasing, which is 15.8% to 16.7%. And we can see here that with increasing cluster size, the binding energy experimental deviation is decreasing. So to identify suitable method and basis set for binding energy calculation quantum chemically, we selected the MP2 augmented CCPV-DZ basis set level of theory without 0-point energy and without basis set superposition error consideration. So why we took this, we can see that the deviation from experiment using this level of theory is 41.6%. Whereas the plus sign indicates the we considered the 0-point energy, and minus sign indicates the without consideration of basis without consideration. So so there are several we took several types of composition by taking considering or without considering the 0-point energy and basis set superposition error using the counterpoise method, but see that the deviation is minimum without considering both. So this happens, and also for water tetramer structure, we used higher method, which is CCSDT method. This is higher level of theory, and our calculated values selected method MP2 augmented CCPV-DZ shows these values. So the deviation is very minimal, but when we consider the basis set superposition error, then the binding energy actually decreases. So it affects the results. But when we average when we average the experimental error deviation from experiment, then it's average out, and we get the value 41.6%, which is minimum using this method. So, and also for a case when hexamer chair structure was used, the binding energy without basis set superposition error is 16.7%. Whereas when we considered the basis set superposition correction, the deviation is 34.6%. So we choose this level of theory without basis set superposition error and without 0-point energy correction. So these are some comparison of our work with the literature values. So here I show H, H2, carbon, nitrogen, oxygen, sulfur, and these are our value. So you can see that hydrogen atom binding energy is 125 Kelvin using water tetramer, and 528 Kelvin of H2 molecule using water tetramer, and water hexamer it is 181 Kelvin for hydrogen and 545 Kelvin for H2. So we listed total 100 species of binding energy of important astrochemical species. You can see in this paper. And now I will discuss some important consequences of our binding energy calculations. So, first is encounter desorption. So we know that water is the main content of interstellar grain mantle, but in dense cloud region there could be some H2 covering the grain mantle. So some previous literature found that the binding energy of H2 on H2 surface is 23 Kelvin, and binding energy of H on H2 surface is 45 Kelvin. But we calculated this on H2 on H2 surface is 67 Kelvin, that is increasing from 23 Kelvin, and H on H2 surface is 23 Kelvin, that is it decreased from 45 to 23 Kelvin. So these are our calculations. And we calculated some important total 96 molecules, 96 important astrochemical molecules, and checked that almost 10 times lower binding energy with compared to water tetramer binding energy. So it has important consequence that you can see that when we consider the binding energy as 23 Kelvin of H2, we get the grain surface abundance of H2 is to 10 power minus 11. And when we consider it 67 Kelvin, then the grain surface abundance is increases to 10 power minus 10. So we also checked some other molecule for like H2O and methanol, and check that grain surface abundance increases with considering this our calculated binding energy on H2 surface. And branched carbon chain molecules, you know that this is the N-propyl cyanide and I-propyl cyanide, and these are already detected by Bellocci et al. 2014, and in Sagittarius B2 region, and they predict by literature, Garrod et al. 2017, they predict that S-butyl cyanide could be a probable candidate for future astronomical detection using their model. And here we I mentioned that these four molecules are the branched carbon chain molecules, and this is already detected, and these are yet to detect or not detected yet. So for the modeling, we used three sets of binding energy. Set 1 is constructed with the binding energy values used in the literature. Set 2 is constructed with some same binding energy values used in set 1, except those 30 species are reported in table 1. So you can see this paper, it will be published very soon. It is already accepted in MNRS. So set 2 is constructed with these values of binding energy, and set 3 is constructed as same as set 2, but rest of the species are used binding energy from KIDA database. So this is the result. These values are our work calculated binding energy on water tetramer surface, and these are the literature values. You can see that these literature values are some predicted values, or and our values are always lower than these values, and for this our abundance is also changed. So we got the values of abundance of you can see that the abundance is 10 power minus 8 for ethyl cyanide, and for set 2 it is 10 power minus 9. And sorry, just a minute. So it dissolves fast than the previous value. So if you see this plot, this is the red is for set 1, and yellow is set 2, and blue is set 3. So with our binding energy, the species dissolve faster than the previous set of binding energy. And also we got using these, including these reactions, this is we considered this abstraction reaction, hydrogen abstraction reaction, and these are our calculated activation barrier. And considering this reaction in our chemical model, we got that tert butyl cyanide could be probable candidate, because you can see the green curve. Tert butyl cyanide is abundance is generating very much. And also we interstellar alcohols and their corresponding reduced aldehyde alcohol, and we did some successive hydrogen addition transition state. First step is we got activation barrier, and second step, this radical reaction, we found transition state, and we calculate binding energy and proton affinity, and we implement our results in our chemical modeling. And from these calculations, you can see that we calculate the binding energy on CO monomer, methanol monomer, H2 monomer, and H2 tetramer. And for CO monomer, the binding energy, if we compare with the H2 monomer, we get 2.85 times lower binding energy on CO monomer. And for methanol monomer, we get 1.16 times higher than H2 monomer. So, and also you can see a point which is the methanol binding energy is always, most of the cases, methanol binding energy is greater than the aldehyde or ketone. So with increasing molecular size, binding energy is also increasing. Okay. So these are my summary. So we approached theoretically or quantum chemically, calculated the binding energy on water surface with increasing cluster size, and got the pentamer and hexamer cluster, the minimum deviation from experiment. So these structure could be used when there is no experimental binding energy values is available to calculate the binding energy or predict the binding energy. And also in terms of average values, binding energy with water monomer is 2.85 times higher than CO monomer and 1.16 times lower than the methanol monomer. And tard butyl cyanide could be a good candidate for future astronomical detection from our modeling. So I would like to acknowledge and thanks the SOC to giving me an opportunity to present our work. And I also would like to thanks my supervisor and our team group mate. And I would like to thanks COSPA for providing financial support. So thank you for your kind attention.
Questions, please. Online questions, please. Then I have a question. So at the beginning you mentioned silicates, carbon, and water.
Yes.
But finally you showed results only for water. So did you do a comparison of binding energy on these three? So different surfaces, silicates, carbon, and water?
Yes, I have shown for H and H2 only. For silicate, graphite, and water, there is comparison.
Okay, and so for more complex, so for other species?
No, we took just water as a grain surface, and because in astrochemical modeling, mainly the binding energy is used with amorphous solid water structure. So for the rest of the species, 100 species, we used only water cluster as a substrate to calculate.
And so you don't have plans to compare on silicates and carbon?
No, actually we did not calculate.
Okay, thank you. More questions? Then we thank the speaker once again. And the next talk is a remote talk by Alec Poliv, radiologist and aromatic